Dr. Sarabjot.
Hanji.
Good morning, sir. Good morning and welcome to this session.
Thank you very much, sir. Thank you for the invitation.
And I also thank you for accepting our invitation and joining in the session.
Not at all. It's a pleasure.
So if you are ready, shall we start?
Hanji, sure. May I share my
Okay,
screen?
sir. Let me introduce you to the audience, then we will start.
Sure.
Okay, good morning, participants. Welcome to this second session of last day of our faculty development program. In this session, we have Dr. Sarabjot Singh Anand, that is the key speaker for this session. Dr. Sarabjot Singh Anand has been involved in the field of machine learning since early 1990 and have worked on the developing algorithms, applying them to real world problems and training a host of data scientists in the capacity of being an academic and entrepreneur. He has published over 90 academic papers on machine learning while an associate professor at the University of Warwick and previous academic posts in the United Kingdom. He has used these algorithms to develop solutions in areas as diverse as pay-per-click optimization, recommender system, prognostic model for chronic illness, diver monitoring using CAN, bus data, cross-selling and upselling products in the financial retail, churn prediction, house price prediction for the telecoms, financial, retail, automotive, manufacturing, and public sectors. His first startup in Ireland won the European IST prize among other technology accolades. Dr. Anand moved back to India in 2012 and co-founded Tetras Data. In 2018, he co-founded Sabut Foundation in Mohali, Punjab, to train engineering students in machine learning and to work on social problems in education, farming, governance, and healthcare. So Dr. Anand is currently adjunct faculty at IISER Mohali and director CSE at Munjal University. So I request Dr. Sarabjot Singh to please address the audience. Over to you, sir.
Thank you so much, sir, and thank you for inviting me today. It's always a pleasure to interact with folks at Punjabi University. Over the 3.5 years that Sabut has been running, we've had a number of students from Punjabi University come to us. I know I'm, of course, talking to the faculty today, in Punjabi University and beyond. But it's always wonderful to be interacting with folks who are interested in this space. I'm just going to share my screen if you can just let me know if it is visible. So today, what I'm going to talk about is a subset of what is typically referred to as natural language processing or natural language understanding or text analysis. Want to bring you into the differences between analyzing data that looks structured like this to unstructured data, which is text. Now, when I started machine learning, I was very lucky to get involved in machine learning in the early 1990s. And the problems we were solving were much simpler at that time than they were today, or they are today. And data was formed in nice tables where each record in the table was an object of interest. So, for example, here I may want to classify people into big spenders and not big spenders based on various input variables, which is what we were given. And at that time, images were not considered to be part of machine learning. It was considered to be a separate area of image processing. Similarly, we dealt with time series data here, where over time you're seeing how a variable evolves, and the objective is to predict what happens next, right? But that was the extent of what we were doing in 1993. Then, of course, the machine learning as a concept came out of the laboratories and came into the real world. And there, what we found was that data was actually much more complex than what we had seen before. And so you had beautifully crafted relational databases but still it was structured data, right? So the whole objective of the work that was done in the mid 1990s was to do feature extraction and to create a representation very similar to what we were seeing or were used to, which is this here. So we were basically joining these various tables. If we were interested in predicting, for example, whether an employee or a customer is going to retransact with this business, then we would create a single record per customer, aggregating over all their orders, the frequency, the recency, and so on, and make predictions. And then, of course, just as we were getting good at this, life got a lot more complicated. For example, Google happened. When I was talking about the 1990s, early 1990s, Google didn't exist at the time. And then, of course, we ended up modeling a lot of data as graphs out here, right? And each of these nodes here was essentially a web page, and the connections between them were essentially hyperlinks between web pages. And so, for example, Google's PageRank was the first search-based algorithm that took into account not just what content was on a page, but also what pages it was connected to. And that was kind of an interesting addition to machine learning. And I remember even back, in the early, even actually the late part of the 1990s, people were already thinking about digital image data, and especially satellite data that was becoming available at the time. Of course, there's video data now, and what has become increasingly available is machine logs. So in my first startup back in the 1999, we had started looking at web logs, which is one kind of log that is created when you are traveling through the internet and clicking on things. We were getting this time series of what are you consuming as a user of the website. And we were building recommender systems to try and recommend content that somebody is interested in based on analyzing their pattern of traversal through the website. And then, of course, what is undoubtedly the largest resource today is text documents, right? And so our focus today is, of course, going to be on text documents and not the others, but I just thought I should set the scene and before we move on to looking at text. And then, of course, to add to the mix, we also have speech data. But again, for the purposes of this lecture, I'm not going to bother looking at the actual speech signal. I'm going to assume that that speech signal has been converted into text, and therefore we now need to analyze essentially text documents. Now, when we look at documents, we have some characteristics of documents that make it interesting. One is that documents can be of different lengths. The other is that a document contains essentially a sequence of words selected from a vocabulary, and that vocabulary is very much based on the person who authored it. So if we think about the lecture I'm giving right now, I'm talking about natural language processing. If Shashi Tharoor was giving the talk today, he would use very different words to what I am using, right? And so the experiences that we have develop a vocabulary. And so while early work that was done on analyzing documents was very dependent on words, and we call that syntactic methods, the realization came to natural language processing researchers fairly soon, that it's not the syntax that is important, it is the semantics. What is it that we are really trying to communicate? Because ultimately, when we think about whenever we are dealing with natural language, really what you have to remember is that natural language is being produced by a human being. And why was it produced? Well, there is a human being here that has some concept, right? And that concept he is trying to communicate, or she is trying to communicate to this other human being. And essentially, this transfer of concepts from one human being to the other can only be achieved as of today by communication. And so the language that is being used here, whether it is for chatbots or whether it is for analyzing blogs or recommending news articles, all of this requires us to get an understanding of what is the document actually about, rather than what are the words that have been used, right? And so the difference between a syntactic approach to analysis and a semantic approach to analysis is, in semantic approaches, we are saying, what is it that somebody is really trying to communicate? Whereas in syntactic approaches, we are saying what words were used. Right? And so we will look today at how we go from a syntactic-based representation of documents, which is very specific to the vocabularies, in which case the speech given by Shashi Tharoor, even though it was on natural language understanding or processing, would appear to be very different to what I have actually spoken to you about. Now, as I said earlier, documents may have hyperlinks between them. So that's really where we are talking about the World Wide Web, where we have a link from one document to the other. And typically, these links are not random. There is a reason why those links have been put by the author of one blog to other documents. And in general, when we talk about natural language processing, we have a very large gambit of technologies that are covered by it, right? And I'm not going to cover all of these, but just to give you a flavor of it, we are not talking about automatic speech recognition. We are not talking about text-to-speech technologies either that convert the text into actual spoken content. We are also not going to talk too much about name entity recognition, but I'm going to give you a flavor of that, where we are trying to identify different important concepts that have been described within text. What we are really going to focus on for now is how do we go from having a document that is unstructured to getting a representation of that document in such a way that we can compare two documents. Okay, so for example, and in fact, I'll come to the examples in a second. But essentially, if we look at this space, we can really say that there are at least three groups of researchers that were interested in this space. The first space of researchers was information retrieval. Right? So these are the guys that made our search engines for us. And why are they interested in this area? Because, well, the idea here is that the user is going to give a query, and that query somehow needs to be matched against this mass of documents here. And the search engine needs to return documents that are relevant to that query. And so the question of how do we define relevance is an important one for us to deal with. The other folks that were also interested in this area were Bayesian probability folks. They were interested in what kind of model can we create that well defines the statistical properties of documents that humans would create. Okay. And then finally, we had the connectionist folks that were basically recognizing the fact that when we communicate through natural language, we are using words. Words are essentially symbols of objects in the real world. So when we look at something and we want to tell somebody what we are looking at, we are going to say a boy, which is a symbol for a male child, is holding a bat, which is, again, understood by the other person because the term bat or the symbol bat can be visualized by humans that have common sense knowledge, right? And so there's a lot of common sense knowledge that needs to be used on the person being communicated to translate the word back into some meaning within their brain, right? And so, given this translation that's required here, and the fact that there is little to no common sense knowledge within computers, what they wanted to look at from a connectionist or a neural computing perspective was how can we, in some way, find numeric or continuous representations of these symbols that allow us to do algebra on it, for example. Right? So all of these people came from different directions and produced different technologies. So what we will see today is things like TF-IDF based representation of words. That was for a long time a key contribution of information retrieval. And we'll talk about what that is. We will also talk about latent semantic analysis. And you will see here, we have already come into semantics, right? What we had mentioned out here. And we are referring to latent here, which is a hidden variable, right? So what we are saying is somewhere hidden within the text, we have these semantics of what is it that is trying to be communicated, right? So that we might have an article that talks about how Virat Kohli played a fantastic knock during this, one-day international being played in Australia, and how he hit, 36 fours and 71 sixes to make India win the match. Now, the point here is that the words themselves don't tell us a lot. What we need to understand is what is it that is being communicated. So it is a cricket match that we are wanting to communicate about the heroics of what Kohli did during that day, for example, right? And so the hidden concepts that are being communicated are referred to as latent variables, right? So you will come across these words, hidden variables or latent variables. They mean the same thing. It is what is not expressed explicitly, right? So when we have some illness, we go to see the doctor. What the doctor sees is symptoms of the illness, but he can't visualize the illness itself, right? And so the illness is a hidden or a latent variable, and what is being observed are the symptoms. Okay, so latent semantic analysis is essentially saying let's get beyond the words, which is what is used in TF-IDF. So TF-IDF is a syntactic approach, and latent semantic analysis is now bringing us into the realm of semantic analysis or semantics, right? Now, of course, the probabilistic folks were also not to be left behind, and so they came up with a probabilistic latent semantic analysis, and from there they actually created what was has been a huge success, which is LDA. Now, a lot of you may think of this as linear discriminant analysis. That's not what we refer to here. What we are talking about is latent Dirichlet allocation. Or the simpler word for that is topic models. Right? So we will hopefully have time to look at what is a topic model as well. How is it different from latent semantic analysis? And then finally, what we're going to do is look a little bit into what are very popular today, which is word embedding. And here you may have heard of things like word2vec, or you may have heard of Glove, and more recently you would have heard about BERT embeddings and Elmo and so on, right? And so all of these, essentially what they're doing is they're taking all the words that we have in the vocabulary and they're giving them coordinates in a high dimensional space. So what you end up with now is the ability to measure how similar one word is to another, right? And so There might be, I'm showing only 3 dimensions because it's not possible for us to draw more than that. But essentially, we have each point in the space represents some word meaning, right? So this might be the word rat. This might be the word mouse. And this might be the word tiger. Now, earlier for a computer, it did not know whether rat is more similar to mouse and mouse is more similar to rat than it is to tiger, right? They were just different tokens or symbols. And so it was difficult for computers to deal with words as such, right? And we'll see how we can utilize these things to do some very interesting machine learning on top of this. But the wonderful thing that the researchers were able to show the validity of these mappings was the fact that if they took the coordinates of king and they subtracted the coordinates of male and they added the coordinates of female, what they got were the coordinates of queen. And this kind of algebra was not possible earlier with words, right? And so this was a major breakthrough that if we can actually define words here in n-dimensional space, typically we talk about 300 to 512 dimensions. But essentially what each of those dimensions defines is how is that word different from another word along that dimension. Okay, so for example, if we wanted to say how different is Germany to India, there might be one of these 300 dimensions that is the dimension of football. And there we would say Germany and India are very far away from each other because Germany has been the world champion multiple times. And India, as of now, finds it difficult to even qualify for the World Cup, right? So the distance along that direction will be very far. But another dimension may be language. And there we know that German actually has one of its roots in Sanskrit. And so Indian languages like Hindi and so on along that dimension will be closer to German than what even French would be. Another dimension could be geographic distance, where again France and Germany will be close to each other, but of course they'll be both equally far from India, right? And so you get the idea that to really be able to understand a word, you need lots of such dimensions that allow you to discriminate between words that have some differences along some dimensions and in other ways are quite similar to each other, right? And so this whole process of taking a document and converting it into a form that can be analyzed by machine learning algorithms, which is essentially a form like this one here, is saying that given a document, we want to convert it into a tabular form, right? Where each document is now one row. There is some objective that we have, which is our output variable. And we have a set of input variables, x1 to xn, right? And these input variables, we are now going to look at how do we create that for a document. But once we have a document in this representation where there is only one record per document, we can feed it into any machine learning algorithm, right? That needs to classify documents, or we want to find out how similar documents are. Once we have this representation, which is called a vector representation, we can do all sorts of interesting analysis of it. And so we are going to look at some of these methods in this talk. We talked about recurrent neural networks. This is a kind of neural network. And we will also see why we sometimes would want to use such neural networks as part of the whole vectorization approach for documents. So let's take a very simple example. Okay? We have a human being that is consuming articles on a website. And the idea here is to create a recommender system for them where we can show them other articles that are similar. Okay. So now in this case, the first thing we have to do is do a vectorization. Now, one way of vectorizing this, of course, is to say, well, all of these words, right? Every one of them could become one of our dimensions. So in representing this document, we would say we could have the word pehle in the first coordinate. We could have bhi in the second column, raha, and so on, right? So every word becomes now a column. And we can start to put a 1 or a 0 depending on whether these words actually appear in the article. Now, why will we have a 0? Because remember, this representation is one record per article. So for a different article, maybe the word pehle does not appear in it. So we will give it a 0. Bhi appears, so we will give a 1. Raha is given a 0, right? And so we end up with a binary vector for each of these articles. And now that we have two vectors, remember the mathematical concept of a vector. I'm showing it in 2 dimensions because it is easier. But if we think of these 3 vectors, right? And now what are these vectors? According to this binary method, they are each point here is not a word, but a document. And we know from vector algebra that a vector has a magnitude and a direction. So if we look at these 3, the magnitude of this vector here, we can calculate by the square of these 2 distances, right? So we know that if this is delta x and this is delta y, then the magnitude is delta x square plus delta y square. What about the direction? The direction is given by this angle, theta. Let's call it theta 1, right? So if we want to know how different are 2 documents, now that we have a representation in this vector space, all we need to do is compare their magnitude and their direction, and we are done. Now, fortunately, we already have a method called cosine similarity. And what is cosine similarity? We basically are saying that the similarity between 2 vectors is the cos of the angle. And it turns out that the cos of the angle is the dot product of 2 vectors divided by the length of the vector. So if we look at that, the length of the vector we know is this. If we divide the vector by its length, what do we get? We get a unit vector. Now, both the vectors are unit vectors because they have been divided by their lengths, right? Now that the magnitude is the same, what is the difference between them? The difference between them is actually this angle alpha, right? Which we are actually calling theta here. So let's stick with theta. And what is that? That's going to be the angle between the 2 vectors. So when will the 2 vectors be identical? They'll be identical whenever this angle here, theta, is equal to 0. And we know that the cos of 0 is 1, right? And so what we are saying is that 2 documents, if the angle between them is 0, they're going to be lying on top of each other. And of course, the magnitude is the same, and so we are done, right? So in terms of content recommendation, a very simple thing we could do is create this vector for every document where every word is an input feature, and we are representing the document by saying a 1 or a 0 depending on whether the word appears in it. And then all we need to do is calculate the cosine similarity, and we will find articles that have essentially a similar set of words being used here, and we'll be able to recommend articles that have a similar vocabulary. Right? Now, of course, what happens if in one article the word BJP appears 100 times, and another article it only appears 10 times? In this binary vectorization, we ignore that information because we only have a 1 or a 0. So instead, what we can do is we can create a count vectorizer, where rather than just having a 1 or a 0, we now start putting in the frequency with which the words appear. Right? So all we are changing is the value that we are storing in the vector. And we have a new way of representing documents. And we can use still cosine similarity to calculate the similarity between these two documents. And remember, the length of the document vector is not the number of words, it is the dot product of the vector with itself square root. Okay, and that is essentially the same as what we have seen here already, where we were saying that here, if D1 has the coordinates x1, y1, we know that the dot product of the document D1 with itself is essentially going to be x1 times x1 plus y1 times y1 squared. Right? So we are getting essentially the, by Pythagoras' theorem, the magnitude of this vector. Right? So that is the length of the document here. So just an important thing to remember. Now, of course, you can argue that just the frequency of a word is not good enough. So if we look at the English language, words like the, and, these are going to be high frequency words, but they are not very meaningful. They don't tell you what this article is really about. Right? And so one of the things that the information retrieval folks did was to create a metric called TF-IDF, where TF stands for term frequency and IDF stands for inverse document frequency. Now, how do we represent that? Well, for a word and a document pair, the TF-IDF score is essentially the number of times the word appears in that document divided by the number of words in the document as a whole times the log of capital N divided by the document frequency of the word. What is N? N is the number of documents in our corpus. Corpus or data store, right? And this here is the number of documents in which W appears. So a word like and is going to probably appear in every document, right? So what are we going to get? We're going to get the log of capital N divided by the document frequency of and, which is also going to be capital N. So we will end up with log of 1, which is 0. And so automatically the words like and the very high frequency words are going to get a value 0. It's not just these words though. Say my corpus consists of only documents about machine learning, then the term machine learning will also get a document TF-IDF score of 0, because every document will have machine learning appear in it, because that's a very specialized document set that we are dealing with, right? So the whole idea of TF-IDF is that words that have a high frequency that were otherwise getting a lot of importance in matching that document with another document are now getting ignored. We're saying that's not important anymore. We are actually giving weight to those documents that have a low those words that have a low document frequency, right? So words that don't appear very often in different documents are getting pushed up, even if their term frequency is not too high, right? So the less frequent words are now getting promoted. And we are basically saying that words that appear many times in this document but do not appear in lots of documents is an important representation of what is this document about, right? And so we have the TF-IDF score. And it's a very simple concept. And actually, we use it very often just conceptually, even when we are vectorizing other types of data other than text also, right? Because we are looking for those things that are important to this object, but do not appear in lots of objects. It's not common, right? So that is the TF-IDF based vectorization. Now, one of the problems with this is that we have these things called key phrases. For example, here we have the word phrase or key phrase, Durga Puja, right? And so, or we have people's names like Usha Thakur, who is one of the infamous people in this article, right? And if we break the article up just on words and tokens, we could have some Usha Sharma here and a Pradeep Thakur as two people that a different article is about. But of course, Usha and Thakur will get a 1 or a frequency associated with how often Usha and Thakur appear, and will therefore not be able to discriminate between a document that talks about these two people and this document that specifically talks about a woman called Usha Thakur, right? And so sometimes what we want to do is we want to utilize key phrases as well in representing our document. Okay, now some people use what are called n-grams, where we basically go through the text and say if we are looking for bigrams, which is really groups of 2 words, we will represent Pichle Saal as one feature of our vector, Saal Navratra as another one, Navratra May as a third one, and so on. So we are creating lots of these bigrams, pairs of 2 words. But the problem with doing that is that the dimensionality of this vector is going to increase, right? So earlier, if there were V unique words, we would have a V dimensional vector. If we go for bigrams and we are allowing every combination of 2 words, we would actually have V plus V squared now as the dimensionality of this vector, where every 2 words now in our vocabulary creates a separate feature. And then if we go to trigrams, we would go to V cube, because now we could have a sequence of any 3 words in the vocabulary appearing in any sequence, and that would be another valid dimension. And so very quickly what we get is an explosion in the number of dimensions that we would be dealing with, right? And so rather than doing that, there are now methods that can be used for extracting key phrases that really are meaningful, right? So Usha Thakur in this case, or United States of America, right? These will be picked out as important groups of words that mean something, And therefore, we would add only those into the vectorization out here. But the truth of the matter, even after we've done vectorization, we don't really know what is the real underlying reason why this person liked this article or spent a lot of time reading this article, right? And so even though we can innovate, we can create new features, we can now add key phrases, we can do named entity extraction where we identify Madhya Pradesh as the location, right? Or Muslim as a community, right? We can do all of that kind of stuff and enrich our vectorization approach. But what we are missing is the underlying reason for why is a person actually consuming this article. They could be consuming it because they're a BJP supporter. They could be consuming it because they're a supporter of this person, Usha Thakur. They could be consuming it because they are from Indore. They could be consuming it because they are either Hindu or Muslim, and those are the two communities that are not too happy with each other in this article. Or they could be consuming it because they're just generally people like me who are concerned about this rising communal hatred in the country, right? And so they might actually want to read other articles and feel more depressed by reading those articles, right? And so that's what we mean by hidden or latent variables, right? And somehow we want to be able to learn the true meaning of why things are the way they are. Let's take another example. Chatbots, right? All of us love chatbots. We love them and we hate them because they're taking jobs away from the call centers. But imagine a chat of this kind that is taking place, where a human says, "Hi, I want to buy a black, fully loaded Honda Accord." Now, we need the bot to respond in some way. And this bot responds by saying, "Sure, have you test driven one yet?" Right? Now, imagine how complex this really is. The first thing is, what does one talk about here? Right? What is it referring to? It's referring to a car. And not any car, it's referring to a Honda Accord. Right? And what is the Honda? Honda is a brand. What is Accord? It's a model. Black is the color. And fully loaded is slang for top of range. And of course, a computer is going to find it very difficult to know all of this stuff. Similarly, test driven is part of the sales cycle. It's one of those things that people do when they want to buy a car, right? So to really be able to respond the way this bot is responding, we need to really understand what the human is really talking about. And so we would use all of the tools that we have just discussed to understand this. The first thing we are going to do is named entity extraction. That's where we are identifying black as a color, Honda as a brand, Accord as a model. Right? We are going to do co-reference resolution. And this is a rather complex co-reference resolution where we are saying this reference to one is to this Honda Accord, which is a car, right? And we are now going to map that onto what is the sales cycle. So somebody says, "I want to buy something." Before, rather than saying, "Yeah, okay, why don't you come in and buy it? We have one in stock." We want to ask them, "Would you like to test drive this? Have you test driven one?" Right? Because we understand that the sales cycle goes from inquiry to test drive, to maybe negotiate, to get finance, to actually buy. And rather than jumping from inquiry to buy, we are wanting the bot to bring the person, the potential customer, the prospect through this cycle to a point of where they can talk about buying. Okay, so we're going to do this co-reference resolution. We are now going to what has said and going to respond. Types of chatbot. One is called a retrieval-based chatbot, where we are identifying what is the intent. The intent here is inquiry. Based on the fact that somebody is inquiring, this response is more appropriate than a response that says, yes, of course, why don't you drop in and you can buy one? Right? So that is what the intent is for. We've defined the entities that we want to extract. Having extracted the entities, if they check the database at the back end, the bot, and finds that they do have a fully loaded Honda Accord, but they don't have a black one, now they can respond and say, well, actually, we don't have a black one, but we do have a red one. And why don't you come in and we can arrange a test drive? And if you like the feel of the car, then we can talk about when a black one would be available for you to buy, right? And so that's why it's important to identify these entities. And when we identify these entities, we can generalize what has been said here. Right now, what has been said by the human is, I want to buy a black, fully loaded Honda Accord. Can you help me? It is being generalized to, I want to buy some color, top range car, right? And so if somebody came along and said, I want to buy a gray BMW, fully loaded BMW, can you help me? The same response could be valid, right? And so we are taking these utterances, what has been said by people, and having converted them into this templatized form, we are then able to search for an appropriate response from the number of responses that have been created within the chatbot. So what are we doing here, right? We are basically saying that we have a pairing of question and answer. And every time a human says something, we first have to find which is the most similar question to what has been asked. So you will go through all the questions, you will find the closest one, and assuming it is close enough, you're basically saying, well, the words may be different, but the meaning is the same as what I have here. So you would then say, can I pick up an answer associated with this question and give that back to the user, right? So what are we doing here again? We are doing vectorization of each of the utterances and looking for whether we have a similar utterance already within our question bank, right? So you can see how even within chatbots, a lot of the things that we have just talked about are being used. A generative chatbot, on the other end, is more difficult. It does not actually have questions and answers. It has a model. And whenever we talk about a model in machine learning, I hope you know that what we are talking about is a probability, a conditional probability of y given x. In the case of the chatbot, the x is an n-dimensional vector representation of all that has been said to date. So if I am trying to come up with this response, the X would be all of this that has been spoken, right? And the Y is now going to be essentially this output here. But this output is not predefined, it is generated, right? And we call this essentially a language model, where we take in what is called the context, which is everything that has been said previously, and we produce one word. We then feed that word also as part of the context and produce the next word, right? So we produce can, that can becomes part of the input. We produce I, can I then becomes part of the input, and we produce have, and so on, right? And so this is where we use some kind of neural language models these days. Whereas earlier we were using things like um, uh, hidden Markov models, or conditional random fields. Okay, and so we are basically using neural computing now to create these generative chatbots. Let's look at another example, semantic analysis, sentiment analysis. Now, what we are doing here is we are given some kind of feedback on a product. And we want to understand whether there are certain aspects of the product, certain features that are getting positive feedback from the customers, some that are getting negative feedback. Now, here again, we're going to do some form of named entity recognition to identify that this is about a phone, to identify that the user interface is a part of a phone. Screen is also a part of a phone, and battery is also part of a phone. So that becomes the named entity recognition piece. Then what we are interested in doing is doing a sentence parsing, where we are able to say that when we encounter the word intuitive, that is really talking about the user interface. When we are talking about sharp, that's talking about the screen, right? So understanding these relationships is important. And then this very is essentially sharp, increasing the sentiment that is being defined about the screen by the word sharp, right? So there is this whole sentence structure that needs to be understood as part of the whole process of saying, do I really understand whether this user is happy with my phone or not happy with my phone? Does very sharp means a bad thing, or is it a good thing? In the context of a screen, it is positive. Long lasting is a key phrase. That key phrase is associated with battery. The negation here makes otherwise positive association of long lasting with battery to actually be a negative feedback. So for all of these things, if we are trying to find other customers that have given similar feedback, we could use vectorization. But part of that whole vectorization process is identifying certain features that we are interested in. Okay. And then as life gets more exciting, we can even utilize stock price prediction by incorporating the sentiment in the market, right? And here we can see that the sentiment in the market was very positive, and we had this large increase in McDonald's price. Here also, we had a very positive sentiment, so we saw an increase. And so you can see how in today's world, where typically when we go to solve a problem, we have textual data, we have structured information, we may have image data, we may have speech data, and we have to bring them all together. by essentially doing some kind of feature extraction. And the key feature extraction that is done in textual data is that of vectorization. Okay, so let me move forward, right? And let's look at a little more into the vectorization itself, because that's what I want to focus on today. Once you get a good vectorization of your documents, you can apply it for lots of different applications, as you've seen already. So let's say we have a corpus of 8 documents. And these documents are very short. They're just titles of documents rather than the document as a whole. But of course, we could be using the whole document here as well, right? And these 8 documents, like we said, we could represent using, as you can see, there are counts here. So we're using a count vectorizer, where for every word in a document, we are representing that word or that document by the frequency with which that word appears in the document. And remember, again, it's the title only that we are talking about here. Now here, an important thing to also remember is that if we had 2 documents that had human-machine interface for ABC computer applications as the first document, and ABC computer applications interface to humans and machines as another title, right? We ignore words like for and the, so we throw them out. We call these stop words. But once we have thrown out these stop words, the representation of the document becomes essentially identical. The sequence with which the words appear is ignored, right? And so we often refer to this representation as the bag of words, where we are saying, yes, a document is a sequence of words, but we are ignoring it. So it's almost like we've taken all the words and thrown them into a bag and we shuffle it up. It doesn't matter. We're going to get the same representation. Okay, so remember, that's called the bag of words representation. If we wanted the TF-IDF score rather than a count vectorizer, all we had to do was to say, okay, in this document D1, we actually had 1, 2, 3, 4, 5, 6 words. Out of that, the word human appears once. So the frequency of the word human in document D1 is 1/6. We then take the log. There are 8 documents, so that's our capital N. And human, as we can see here, appears in 2 documents in our corpus. And so we would go 8/2, the log of that, and we would end up with a score of 0.23. So if we were using a TF-IDF based vectorizer, we would actually have 0.23 here rather than 1. Okay, so one move from, I won't go deep into the maths here. You'll have to do it in your own time. But essentially, the idea that people came up with, and I'll go to the idea itself first, is that whenever we have our count vectorization done here, what if we were able to do a matrix factorization? Right, where let's call this matrix X. We were able to represent it as the product of 3 matrices, U, V, and sigma. And if this here is an N by M matrix, where we have N words and M documents, if we had U as N by K, this is K by K, and this is K by M, In effect, what we are saying is that U here is a k-dimensional representation for every word. And M here is the number of documents, and the documents are also represented in that same k-dimensional representation. So what we are then going to get when we multiply these three is a reconstruction of X. Right? When we multiply these. Now, we haven't talked about how we get these U's and V's and sigma, but if we ignore that for now, and we say that this is a diagonal matrix, this actually kind of becomes interesting, right? And so out here, the maths is really based around principal component analysis. And I don't have the time to go into what principal component analysis does, but very quickly, if we have data that looks like this, it's two-dimensional data, originally represented using attribute 1 and attribute 2. Principal component analysis finds a linear transformation, right? So each of these is a linear transformation. In such a way that the first principal component now captures the majority of the variance in the data. And the second principal component represents less variance than the first one, and the third one, if there was a third one, would represent even less of the variance. Compare that with the original representation where the variance along both of these was actually very large, equally large almost, right? Now it turns out that the way in which we can calculate these principal components is to do what is called an eigenvalue decomposition of the covariance matrix of the data, right? So what we are saying is the data here consists of attribute 1 and attribute 2. We take all of this data, and it's an unsupervised approach. So we are not taking into account what are we trying to classify the data into. But we compute from that the covariance matrix, which is going to be a 2 by 2 matrix. And we do an eigenvalue decomposition of this, right? So the 2 by 2 covariance matrix, this is going to be the variance of attribute 1. This is going to be the variance of attribute 2. And this here is the covariance of attribute 1 and attribute 2. And so the value in here is the same as the value in here. So it is symmetrical around the diagonal. And we do an eigenvalue decomposition. And just to remind you that if you have a matrix X and we multiply that matrix with V and we end up with some scalar times V, that is referred to as an eigenvector. And it turns out that we would get two eigenvectors for this 2 by 2 covariance matrix, and we will get two different lambda values as well, and those are called the eigenvalues. And it further turns out that the eigenvalues is the amount of variance captured in that direction of the eigenvector, right? So the eigenvectors are these, this direction, and this is the second eigenvector. the amount of variance captured is the scalar here, which is the eigenvalue. And so once we have done a eigenvalue decomposition of this covariance matrix, and of course it makes sense really only when you have very high dimensional data, and in text we have very high dimensional data, right? Because every dimension is every word that is in our corpus. So that's a very high dimensional data, maybe 65,000, maybe 100,000 words, or even larger than that. And so to reduce the dimensionality, one way that we could use is to compute the covariance matrix and do principal component analysis on it, right? And with the principal component analysis that we do, because each of the principal components have a eigenvalue associated with it, which represents the variance, we can throw away some of the low variance eigenvectors, and that's how we reduce the dimensionality. So in this case, it turns out that this whole method called singular value decomposition is a kind of a parallel eigenvalue decomposition that happens. And we do a singular value decomposition of the matrix X. But in effect, what we are saying is that this vector, the matrix V that we referred to here, is the eigenvalue decomposition, or the vectors of the eigenvalue decomposition that we have done of X transpose X. At the same time, it turns out that our matrix U is the eigenvalue decomposition of X transpose, this one here, right? And we end up with this decomposition of X consisting of the multiplication of U, V, and this here, which I was showing as sigma on the other slide, is the diagonal matrix consisting of the eigenvalues. So this is our U, this is our V, and this is our diagonal matrix of eigenvalues. And you can see that the eigenvalues are going down in this direction. And again, what they represent is the amount of variance of the data that has been captured along each of these directions. And so by going down here, we could decide on whether we should stop and represent this data. And remember that this data has 1, 2, 3, 4, 5, 6, 7, 8, 9 dimensions here, right? So we can reduce the dimensionality by saying, okay, if I add up all of these values and divide by the sum of all of the diagonal elements, I get to know how much of the variance, what percentage of the variance is being captured by the first 1, 2, 3, 4, 5, 6 dimension. And as long as we have captured around 85% of the variance, we typically then can ignore these, right? But of course, if we want to visualize the data, then we really have to limit ourselves to 2 dimensions. And of course, we can see that 2 dimensions is not capturing a lot of the variance, because approximately this is around 6, and we have, 4, 5, 6, 7, 8, probably 9 out here, right? And so what is being captured is only 6 out of 15, which is nowhere near the 85%. But by limiting it to a 2 by 2 dimensions, what we are really saying here is that every word is now represented in a 2-dimensional space. So this is the word human. This here is the word interface. This here is the word computer. This one is the word user, right? And so we now have a 2-dimensional representation of every word in our vocabulary. The same way here, we have a 2-dimensional representation of every document instead, right? And so we can visualize now the 2 dimensions here. And we can see that the words seem to group up, a few of them here, a few of them here. This seems like a bit of an outlier. And if we look here, the documents are fairly spread out, but again, there seems to be 2 clusters of documents that exist. right? And what are these dimensions? These are our latent variables. We don't know what they mean, but we do know that somehow they capture a lot of the variance in the original data. And when we multiply now this 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, this 12 by 2 matrix with this 2 by 2 matrix, which is just this part here, and then multiply this 2 by 8, I think 1, 2, 3, 4, 5, 6, 8, 9 documents, right? I'm actually now getting a 12 by 9 matrix, which is actually what I had here, right? So I have 9 documents and 12 words. I am getting this reconstruction of this matrix. And what is interesting is that earlier we had a very sparse matrix where we were saying document 1 has nothing to do with user. But now magically user has a positive value associated. And of course, we know that when we talk about human interface of a computer, we are really talking about the user of the computer. And similarly, when we talk about system, the user system response, then system here is actually referring to computer as well, right? And we are taking those correlations into account and now have a representation here that is non-sparse, right? And is taking into account these relationships and increasing the value of words that are related to other words in this document. So this document was about human-computer interface. It has actually associated with it user system response, right? And now when we look at these documents, we can see very clearly that all of these documents for the vocabulary up here has positive numbers. These 4 documents have negative numbers associated with this area, or small numbers comparatively, right? And we can see that the data has actually got clustered into 2 parts. And it turns out that if we actually look at these documents that we were clustering, these are all to do with human system engineering, right? And response time and so on. These ones here are about graphs or graph theory. So they are very different, and that difference has been captured by our new coordinates that we have created. Okay, and this is the first semantic vectorization, where we have gone from having for every document a 12-dimensional representation, which is this one here, right? This is one document's representation. We have now gone to, for each document, having only a 2-dimensional representation. But remember again, we don't know what these dimensions truly mean. Okay, so this is the first attempt that was made at representing the semantics of a document instead. Now let's move to a probabilistic approach. And there we are going to talk about latent Dirichlet allocation. And in particular, what we are interested in doing there is doing something similar to what we did in locality sensitive, latent semantic analysis, but more from a probabilistic approach instead. Okay? So what does that look like? So as we said, the whole idea here is to deal with distinct vocabularies of human beings that are authoring documents. So a language has a vocabulary. The words from the vocabulary are chosen to form a document. This is the basic generative process that we are assuming takes place within the mind of the author of the document. Words are chosen by an author, and different authors could write the same article using different vocabulary. And so we assume here that the words in a document reflect a mix of unobserved or latent topics. And what is a topic? A topic is essentially a probability distribution over all the words in the vocabulary. So for example, we here have a topic which we have named government union. Why have we named them government unions? Because the most probable words within this topic are Sarkar, Karmchariyon, Pradarshan, Mang, Adhyaksh, Dharna, and Andolan. And these are words that we would typically associate with some trade union kind of activity. And the fact that we are talking about Karmcharis, with employees and of the government, therefore, we came up with this name called government union. Remember, I said we came up with this name. So this name is not being defined by machine learning. What is being defined by machine learning is this probability distribution. It is being estimated by machine learning, right? So the input is a set of documents, and the output is the set of topics, firstly, that describe the different topics that exist in an unobserved way within the documents. And the second is a vector for every document. So what you can see here is that we have said that there are 11 topics. I have shown 4 out of those topics to you here, right? The second one is agricultural pricing. The third one is cricket. And the fourth one is weather. And what we are saying here is that document 0 has a probability of 0.19 of a word being generated by topic 4, probability of 0.16 of a word being generated by topic 5, probability of 0.36 of a word being generated by topic 6, and 0.28 of words being generated by topic 9. So you can see one big difference between this vectorization and what we saw in latent semantic analysis was that in latent semantic analysis, we could have negative coordinate values for documents. And these, to think of them as how important is a topic to this document is very, very difficult, right? We could say that this is topic 1 and this is topic 2. And we are saying the importance of topic 4 with K, but 2, 3, what does that mean, right? It was difficult to interpret this. What we are here saying from a probabilistic perspective is something much nicer. We are saying that if we have a document and we have a set of words in there, 19% of the words will be generated from the probability distribution associated with topic 4. 16% of the words will be generated by the distribution across the vocabulary of topic 5. Similarly, 36% will be topic 6 and 28% will be topic 9. So it's a very easy interpretation, right? Similarly, when we say words are generated by these words are going to have a much higher probability of being in T0 than cricket, agricultural pricing, or government unions, because their probabilities are 0, right? And so the highly probable words in here are less likely to be in this document. So what we have done there is we have said that the words that are in the document depend on an underlying probability distribution across topics, and each of those topics has a probability distribution across words. And so the generative process in LDA, or latent Dirichlet allocation, is, we say that when we sit down to create a document, we first decide on the length of the document, and we use a Poisson distribution where the only parameter lambda can be estimated from our document repository, right? We know how to do that. From a frequentistic perspective, we can just look at what is the number of words in each document, and we can take the average number of words in a document, and that would be our lambda. So from our corpus, we have learned this. So whenever we generate a value from this Poisson distribution for the new document that's being generated, that document will have a length that is to be expected. Once we have chosen the document length n, we now have to decide what is the topic mix of this new document, right? So here we have decided 7% T1, 19% T2, 34% T3, 38% T4, and none of the other topics have an impact. Now, this is where the word Dirichlet comes in. The Dirichlet distribution, and that to a k-dimensional Dirichlet distribution, is a probability distribution where when we sample from that probability distribution, we actually get a categorical distribution. In effect, what we are saying is whenever we sample a valid value from a Dirichlet distribution, we get a set of numbers that adds up to 1, right? And when we are saying a k Dirichlet distribution, out here k is equal to 11, right? So what does that give us? This gives us the probability distribution for every topic generating word. So what we have done in effect is to say we had a document. We have a number of empty slots that have to be filled in by words. The number of slots here is n, which is the length of this document. And again, to remind you, this is the length of the document now in terms of words, not in terms of vector dot product. Okay. And now what we are doing here is we have created a categorical distribution of across all the topics. And now we can sample from this categorical distribution. And we get to allocate that this first slot in my document will be filled by topic 1. The second slot may be filled by topic 5. The third one may be by topic 6. What we are doing is we are using this distribution that we have got from the Dirichlet distribution. And we are defining now that 7% of the slots will be from topic 1, right? 19% from topic 2, and so on. So we fill in these slots. And once we have decided on these slots, which is what I'm saying here, we have our beta parameters, which is number of topics times vocabulary size. So we essentially have this here, right? We can see that this is V times 4 because there are 4 topics, right? So we are just flipping it around. We are taking the transpose of it. We are saying K times V. And so now to generate a word, what we are taking is the beta parameters into account that assign probabilities to every word within a topic. the choice of topic that was chosen here to fill this slot, and we produce a word out of it using this probability distribution. And this is the generative model that we have chosen. Of course, we don't have the time to get into how this model is learned from data. We have talked about how do we create documents. Now we are assuming that all the documents in our corpus have been built using this generative model. So from the data now we are going to learn all of our parameters, the alphas and the betas, that are going to give us the probability of every word within a topic and the associated topic vector for every document, right? And that is our LDA vectorization approach. I won't get into the maths. The maths is a little too complex for us to cover today. But essentially, you can see that very similar to what we got here in singular value decomposition, where we had our matrix X, we converted it into the product of three matrices, where the matrix U assigned a coordinate, a set of coordinates to every word, and the matrix V assigned 2 coordinates to every document. Similarly here, we are talking about having 11 topics instead of 2, but every document is assigned coordinates in this 11-dimensional space, with the added advantage that it's easy to interpret because this is a probability distribution. So this is our V matrix, and this here is our U matrix that maps every word onto a probability assigned to every topic, right? So you can see the similarities between these two methods. So we're kind of running out of time. So what I want to do is move on to a very interesting piece, which is on the neural computing side of things. And so when these researchers in neural computing sat down and said, hey, we have a problem here. We have the two words toad and frog, and we don't know whether toad and frog are closer to each other or toad and tiger are closer to each other. Why? Because whenever we have categorical data like this, like words, we convert it into a one-hot encoded vectorization, right? And so every word gets mapped onto one-hot encoded vector, where there must be some element of this vector that corresponds to the word toad, and that will have a 1, everything else would be 0. And similarly for the same vector length, because the vector length is determined by the size of the vocabulary, there'll be some element here which is frog, and that will have a 1, everything else will have a 0 when we encounter the word frog. And tiger, again, we would end up with, in this V-dimensional space, potentially a 1 here associated with the element of the vector, which is the tiger. So here, it turns out that the tiger's index is closer to the toad than to the frog. But that doesn't mean that the tiger is more similar to the toad, right? And so they wanted to find a better way of vectorizing words. And the thought that came to their mind, this is some researchers from Google, was the fact that, they were always told by their parents that you will be known by the company you keep. So keep good company, hang around with good people. So they said, hang on a second, maybe a word could be known by the company. And what they meant by that was, they said, well, imagine if we have a huge corpus, lots of documents. And we go through the documents, and for every unique word, for example, here we are saying stays, we look at the words that appear in the context of that word. And by context, we are saying the words on either side of the word stay. And how many words? That's the window size for the context. Well, that's a hyperparameter, right? So we can define that in advance. But once we have defined that the context is 3 words or 5 words or whatever, we stick to that representation. And so the idea here is to say that in our corpus, every time I see the word stays, let me look at the words on the left and the words on the right. How many words is determined by the window size, which is a hyperparameter of the algorithm. But now, if the word rat has a distribution across all words in my vocabulary, and what is this distribution? It is how often these words appear in the context of stays, when stays is the center word of focus. And so the idea was that if we can actually see for every word what is their distribution, maybe we can learn a function that, given any word, predicts what is the probability of another word in the vocabulary belonging to the context of the word. Right? And so what they said was, let's estimate the probability of any word in the vocabulary given a particular word, WC, as the center word. And what do we want to do? We want to estimate it in such a way that we maximize the probability of words that are observed in our corpus as being in the context of our center word. So all of these words that have been seen in our corpus, let's increase their probability of occurring, right? And we are learning a function. So what does that function look like? It looks like this. I'll come back to what this is, but well, actually, let's start talking about it. So what we are saying here is we have a one hot encoded center word that is input from here. So for example, here we said the word stays is our center word. So say this node here was corresponding to stays. So we will input a 1 in here. All the other words will have, nodes will have an input of C. Now this is nothing but a multi-layered perceptron. Where we have an input layer, we have one hidden layer, and we have one output layer. And the activation function for the output layer is softbanks. So this here is going to be the probability of word 1 being in the context given stays is the center word in this context, right? Because we put in stays as our input vector. And similarly, for every other word, we would have this probability being defined, right? Because we've used the softbanks. I'm presuming that you all know about neural networks. So we have a weight matrix that connects the input layer to this hidden layer. And we have the weight matrix that connects the hidden layer to the output layer. And you can see something quite fascinating happening here. The weight vector that connects the input layer to the hidden layer is V times D. So typically what we have is we have a bias out here. We are saying there is no bias. So ignore the bias. So essentially what we have in W1 is for every word we have a d-dimensional vector. And when we multiply it by a one-hot encoded vector, then essentially what we are saying is that we are multiplying this whole thing piece here with this 0, 0, 1, 0, right? So this is V times D. We are going to multiply a 1 times V with it. And what will we end up with? A 1 times D. So we end up with this hidden vector representation, which is a d-dimensional representation. And what is that d-dimensional representation? If this was the kth input, then basically what we are saying is that the wk, which is the kth vector in here, is really being output out here, right? So we basically that multiplication with this one hot encoded vector is really choosing the appropriate vector out here. So we can think of this as being a d-dimensional representation of every word given that it is a center word. This is the representation of stays whenever it is a center word. So we have now got this d-dimensional representation and we are multiplying it by a d times v vector. This here is a 1 times d vector, right, coming out of here. We multiply it by w2, which is this. And what do we get? We get a 1 times v. So now we can say that W2, right, this was W1. W2 is d-dimensional and has v such d-dimensional vectors here, where each column here now corresponds to one of these output nodes. So this would be a d-dimensional representation of the word W1 whenever it is a context word, right? Because what we are saying is, what are we doing here? This is our, let's call these vectors u, right? So u1, u2 to ud, oops, ud, and we are multiplying it by v1, v2 to v2, right? And so the output that's happening here is e to the power of u times v1. This is uk dot v1, where uk is the center word representation of stays and v1 is the context word representation of the first word in the vocabulary, divided by the sum of e to the power of uk dot v j, where j goes from 1 to 2. Right? And that's what the formulation of this machine learning problem is. What we are saying is that for every word wi, we have two vectors. This is the center word representation of this word, and this is the context word representation of this word. And we define the probability of a word O appearing in the context whenever C is the center word as e to the power of the dot product of these two vectors divided by the sum across dot products of VC with respect to all of the UIs that are used here, that can appear within the context. So this is essentially softmax. And what are we doing here? Every machine learning algorithm needs a cost function. So what are we saying our cost function is? We want to learn these parameters, our U and V vectors, which is what we are representing as theta here, such that the probability for every word that appears in our corpus, given that word, for every word that appears in the context, and the context is of size k here, right? So we are multiplying here, where we are saying that each of the words that appear in the context are independent of each other, right? So by multiplying all these probabilities, what are we getting? This part here is the probability of one input row into our machine learning algorithm, right? One row here is where we have one selected center word and our context associated with that center word. So for every instance that goes in, of which we are assuming we have t such instances that are independent of each other, we are wanting to maximize this probability. And this is based on the maximum likelihood principle. Okay, but essentially again, what we are saying is that we have taken this representation, the textual representation, and we have created an X matrix, which we have again now created a decomposition of into two matrices, one which is M by D and the other that is D by N. One that represents each word as a center word and the other that represents each word as a context word, and we have M is equal to N in this case. So what is this X matrix? It's this, where we are saying this is the center word and this is the context word. And we are creating this co-occurrence matrix by saying that whenever we have human, we have interface within its context. Whenever we have interface, we have human, computer, user, and system and machine within the context, right? And what data are we looking at? We are still looking at this data here. Very small data. Here. Right? And we are essentially doing the same thing. We are saying whenever we see machine, there will be interface, there will be human out here, there will be does it appear again? Or when we see human here, we see system and we see engineering, right? And so we are creating the same kind of the same idea and producing a matrix of this kind. where we can see the contextual words associated with each of these. And we are doing a matrix decomposition, right? So the basic idea comes back to the same, that given our input data, what has changed here in latent semantic analysis or singular value decomposition, our X was where every document was the context of every word. The whole document was the context. Now what we are saying is we are limiting our context to be only maybe 2 or 3 words on each side of the word. And that's why we end up, rather than having a document to word matrix, we are now having a co-occurrence matrix where these are the context words that appear whenever this is the center word, right? And this essentially is the basis of word to vec, it is the basis of love, and that creates this kind of representation where we have reduced the dimensionality to 2 dimensions to see, but we can see that these are all countries. These are all animals. They're far away from the different types of drinks, right? And we have different types of food here, and we have education related words out here. Right now, you would say, hang on a second, pizza is not a drink. Why is it closer to brandy than it is to meatballs? And that's a valid question, right? And all I want to say is that remember, we have taken what is 100 or 300 dimensional word vector, and we have reduced it to 2 dimensions. So we have lost information here. So the inaccuracies you are seeing here are more with the dimensionality reduction we have done later to visualize this data than to do with the actual vectors themselves. So now that we have these words, how do we actually create a vectorization of a document, right? And we had said that when we have documents, we can convert that into vector form where we have for every document, we have our words. And we have our TF-IDF vectorization that may happen here, where the TF-IDF value here is telling us how important is this word in describing this document, right? And what else do we have? We actually have now a V by D dimensional representation where we are saying all of our words, of course, are now represented in this D-dimensional space by something like word to vec. And if we multiply these 2 matrices, what do we end up with? I'm going to multiply my TF-IDF for word 1 with word 1's vector. And I'm going to end up with a N by D dimensional vector, where every document is now represented in D dimensional space, right? Because we will, when we multiply this, we will multiply this with this, then we'll multiply this with this, we'll multiply this with this, right? And we are ending up in doing that multiplication, right? We are ending up with this representation here, this D-dimensional representation for my document D1. And I'm essentially taking a weighted average of the vectors here, sorry, not this one, of all of the words where the weights are the TF-IDF score. So the higher the TF-IDF score, the more weight is given to this vector in computing this here. And this now becomes a document vector. representation. In again D dimensions, and what are those D dimensions? We don't know. But what we are saying is there must be some semantic relationship that occurs there. So remember that in all of these semantic representations, we don't really know what these represent, but there is a belief that these will represent some meaning. Each one of these will represent some direction of that meaning of the words or the document, and therefore they are referred to as latent variable. One of the great advantages of this is that here we have a very sparse representation of each document, because in a document you may have 2000 words, and there might be repetition of words in here also. So the number of unique words may be 600. Our vocabulary is probably 65,000 or even larger than that, maybe 1 million, right? And so most of the data here is zero. It doesn't appear within the document. Whereas out here we have a dense representation, and typically D is much smaller than B, the size of the vocabulary. So what we have managed to do is also squeeze down that representation, get a much more compact representation, where the document's similarity with each other is now not limited to just the words that have been used, right? Just as we had seen in latent semantic analysis or topic models, we are now saying, using these word embeddings also, we have a representation of the document, and so we can calculate much better similarity between documents, because the words don't matter as much as the hidden topic, right? Or the similarity in meaning of those documents. Now, we are out of time, but just to give you an idea of what happens with using recurrent neural networks in the mix, is that all of these methods, whether it is the embedding based methods or the topic modeling based probabilistic models or the information retrievals, latent semantic analysis, is we are ignoring the sequence of the words that are being spoken or written in the document. And the recurrent neural network actually captures that. So with a neural network of this recurrent neural network type, what we are saying is that every word is fed into the neural network one by one. So we might put in the word the, rain, stays, mainly, and so on, right? It's feeding one word at a time. And what is happening here is a memory update function where the output is supposed to be a representation of everything that has gone on in the past. So we put in a dummy history to start with, and as we feed in one word at a time, this history gets updated. And the output here then becomes an embedding, similar to what we talked about here, word-to-vec embedding, but is an embedding that is taking into account the sequence in which the words actually occurred. Okay, and this process has been used in another vectorization approach called ELMO. I would recommend that you read that. It makes a very interesting feat. And then finally, one of the big problems with recurrent neural networks is that, remember, we have to learn the parameters using something like backpropagation. And whenever we have to learn backpropagation, now we are going with this backpropagation through time. And we have a problem called vanishing gradients. right? Remember that backpropagation updates the weights in the neural network based on the gradient of change in cost function. But these gradients, if they are very, very small numbers, as we get into deep neural networks in general, so you would have heard of this even if you have done something like convolutional neural nets, you will essentially end up multiplying a lot of small numbers. And so the change that happens to the weights because of the early part of the sequence of words is actually very, very little. And they have very little impact. And so when you talk about things like BERT, you are changing the paradigm and you're saying that these are attention-based models. Attention-based models, or what are now called transformers, that don't take into account the sequence explicitly like the recurrent neural network is doing, but it does still gather what is interesting within the history of what has been provided. Okay, unfortunately, of course, this is a very big topic and people have spent months learning natural language processing, not 2 hours. So I won't be able to get into the detail of that, but I hope if nothing else, this 2 hours that we have spent together has given you a flavor of what it means to vectorize text. And that is the basic operation that is done before we can do any kind of downstream analysis. If you can't represent and understand why one representation is better than the other, you're not really going to be able to do any useful natural language processing, right? And so I hope that this journey has been interesting. Remember, we are saying that when we're given documents, we want to represent them as a tabular form, in a tabular form, which is really a vector form. The simple methods are based on vocabularies, are vocabulary-specific representations that we refer to as syntactic representations. There we have a binary vectorization, count vectorization, and TF-IDF-based vectorization. And then what we look at are these semantic representations that say, but words are an artifact that depends on who is speaking. And so if Sarabjot is speaking, he's using some words. If Priyanka is speaking, she'll use some other words, or Ankita will use another set of words. But if all three people are talking about natural language processing, humans are able to do that mapping to say, okay, what they say all talking about is natural language processing, but computers were not able to do it using these syntactic representations. And so they moved to semantic representations, and we have seen a whole host where mathematicians, information retrieval folks, and neural network folks, neural computing folks have applied their own thought process to this and have come up with some fantastic advancements in this area. And that's why we are seeing so much advancement in the applications of natural language processing within the real world today. Thank you very much. And I do hope that this has been useful.
Thank you, sir. Thank you very much for this elaborative session. Any questions from the participants? Anyone want to ask any question? Have any doubt? Then can please ask to the sir.
So either everybody already knew this, or I've lost them here. But by all means, connect with me, later through LinkedIn or whatever. I'll be happy to, provide answers to any questions you may have in the future also.
Yeah. Thank you, sir. Thank you for this elaborative session. Basically, word embeddings are based on many text processing tasks are based upon this particular word embedding, and you have nicely explained the need of converting the text into embeddings, and also demonstrate how we can create the embedding from you can say text. So embedding can represent varied features of word, and it's associated with other words in context. So you also explained its application in various use cases like document similarity, etc. And I am very much sure that participants may have listened these words earlier, because whoever working in the text processing, he may listen these words, but your explanation definitely improve their understanding about the concept. So thank you once again, sir, for such a wonderful session.
You're
That's
very
all
welcome.
from
Thank you.
my side. Thank you. Some participants are requesting your email ID.
So I'll just type it in here. There we go.
So email ID of sir is available in the chat window. All the participants who need it may note it down. Okay, thank you, sir. Thank you very much. So now we are going to conclude this session. That is the last session of this faculty development program. In the next session, we will again meet together at 2:30 p.m. and we will have a exam. We will have a small quiz that is based upon all the sessions and followed by our valedictory section. So please join back at 2:30 p.m. Till then, thank you. Goodbye.